a three-dimensional vector space, which is the subspace of set of all two-way matrices, which is a four-dimensional subspace. Set of all antisymmetric matrices is a subspace of, is a one-dimensional subspace of set of all two-by-two matrices. Okay? Set of all points in a given plane that is passing through the origin is a subspace of three-dimensional vector space. Set of all points on a line is a subspace of two-dimensional vector space. Like that. So you have subspaces defined in such a way that they are also as we define. It's also a vector space. Let me define one more quantity called span of a set of linearly independent span of a set of linearly independent. Let V1, V2, etc. Vm be a set of linearly independent vectors in an n-dimensional vector space. That M is less than n. I cannot have set of linearly independent vectors with M greater than n, because largest number of linearly independent vectors in this space will be n only. So I can consider a smaller number of linearly independent vectors than the number of elements in the space. Then span of these vectors V1, V2, etc. Vm, span of this set is defined as set of vectors C1 times V1 plus C2 times V2 plus etc. Cm times Vm, such that C1, C2, Cm belong to L. I am going to define this in this fashion. Since V1, V2, etc. Vm are linearly independent, okay, Vm, V2, V3, etc. are linearly independent, this set of possible vectors for different choices of this Cm, C1 to Cm will give me a vector space. So span of linearly independent vector is always a vector space. In fact, that is a way to construct vector spaces. You can construct different vector spaces by taking span of linearly independent vectors. Okay, so this is a vector space. And what is the dimension? The span is a definition by which, in a controlled way, you can construct vector spaces of a given dimension, subspaces of a given dimension, vector spaces of a given nature, subspaces of a given nature, and so on. So, this is an m-dimensional. So, the span is an m-dimensional subspace of the n-dimensional vector space. M-dimensional subspace of the n-dimensional vector space. So span of any set of linearly independent vectors, so span of linearly independent vectors is a vector space. The dimension is equal to number of linearly. In fact, the linearly independent set of vectors that we have considered itself will become one of the bases for this. For example, if I take span of one zero 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 0 1 1 0 0 0 0 1. If I take span of this, what will I get? If I take span of this, what will I get? Set of all. I get a three-dimensional vector space, but what are those vectors? Each vector is a symmetric two-weight matrix. This is set of all symmetric two-weight matrices. Okay, so this is set of all symmetric two-weight matrices. Similarly, if I take span of 0 1 minus 1 0, this is set of all 2 by 2 skew symmetric matrices. And if I take span of 1 comma x, this will be set of all straight lines. Okay. So whatever vector spaces that I have discussed from morning can be viewed as span of some basis elements. You take a higher vector space,